So question 36 is a bit of a challenging question, right? They've given us vitamin C. So I've got vitamin C, and they tell us it's a weak diprotic acid, right? It's a polyprotic acid, and that it can donate more than one proton. But as we'll see in a second, right, the first ionization is 6.8 times 10 to the minus 5. The second ionization is 2.7 times 10 to the minus 12. Basically, the second ionization of vitamin C is so small, right? That concentration is going to be so small that we're going to get from that we can ignore, right? We can ignore the second Ka value and just focus on the first Ka value that we have for that vitamin C. And then we're told, right, we're looking for the pH of this solution when we dissolve. What's our mass that we're dissolving?
Can you go over why you can ignore it here?
Yeah. Got 10.4 milligrams, and we're dissolving that in 1 milliliter. And so, yeah, we can ignore that because we can go through the calculation and show that basically 10 to the minus 5 is a pretty small number. 10 to the minus 12 is even smaller. So when we're going to do the calculation, right, Ka equals hydronium times the conjugate base all over the concentration of my acid. So the first calculation for Ka1, we're going to use our first concentration and then have x squared on top. For the second calculation, we're going to use of that concentration what ionized. That's going to be a really small number. And then be very similar for Ka2, right? We're going to use hydronium again. Now we've got A2 minus because we've lost 2 protons all over A minus. So this number came from up here. It's going to be really small. This is really small. So we've got x squared, right, equals that small number. Take the square root of this, take the square root of that. You're going to get an even smaller number. That basically, we can find that concentration. When you go and take the negative log and the pH from that, it's not going to change your pH because the concentration is so small. Because that Ka, 10 to the minus 12, is an incredibly small number. So that's how we can ignore it. Really, the first one is going to be what has the impact on pH. And if the next one is 1,000 less or more than that, you can ignore it. So if we're 10 to the minus 8, we can ignore that because it's more than 1,000-fold smaller. We're 10 to the minus 12. So that's even more than 1,000 smaller than our initial Ka value. So it's because it's that 10 to the minus 12 that, yeah, we can find that concentration, but at the end of the day, that concentration, it's not going to change our pH. So the other problem here with 36 is they've given us mass and constant and volume. We have to find concentration, right? So a little bit of review of Chem 106, right? Concentration is molarity, moles per liter, and we have mass currently and volume. So I need to turn the 10.4 milligrams, right, into grams. I know there are 1,000 milligrams in 1 gram. So I've got 0.001, no, got more than that. 0.10, yeah, grams of vitamin C. Now I need to find moles of vitamin C, right? So I know if I've got 1.014104 grams, I know for every 1 mole of vitamin C, right? You go Google vitamin C, the molar mass of vitamin C is 176 grams. So grams cancel out, and we're going to be left with moles of vitamin C. So divide that by 176, and I get 5.9 times 10 to the minus 5 moles of vitamin C. We need concentration, which is moles per liter. So I've got 5.9 times 10 to the minus 5 moles of vitamin C. And I've dissolved that in 1 milliliter, which is 0.001 liters. So we divide by 0.001, and I'm going to get 5.9 times 10 to the minus 2 molar. Yeah. So there's my concentration of my acid, right? I know the Ka, I know the concentration of my acid now. Now I can find hydronium and the conjugate base, and now I can find pH. So we'll get started on that, right? The Ka, 6.8 times 10 to the minus 5 equals, don't know hydronium, don't know the conjugate base, but they should be the same. So X times X over the concentration that we just found, all right? 5.9 times 10 to the minus 2. So I'm going to multiply both sides by that. So I'm going to multiply 5.9 times 10 to the minus 2 over here. And I'm going to do that over here as well. All right, I get x squared equals, that cancels out, so times 6.8 times 10 to the minus 5. I get x squared equals 4.02 times 10 to the minus 6. Square root of that, and x equals 2 times 10 to the minus 3. What was x, right? Long ago, we plugged x in. X is my hydronium concentration. So now, right, that was step 4. Step 5, pH equals negative log of my hydronium concentration. pH equals the negative log of I get a pH of, so my concentration, 2.00 times 10 to the minus 3. pH equals 2.697. So I would say 2.70 for a pH for that, Zoe, for your question. So be careful. The mass might be different for yours. The steps would be the same. We're going to convert mass from milligrams to grams, and then grams to moles using the molar mass, right? Vitamin C has got a molar mass of 176 grams per mole. Once I find the moles, I can find concentration, because concentration is moles per volume, moles per liter. And then once I find the concentration, then this is our, the problem that we've practiced a few times now. Given concentration, given Ka, what's my hydronium concentration? What's my pH from that? So yeah, a little bit of an involved problem, to find concentration first before we find the pH of that solution.